I should present it at the optical physics group. But then you see, I'm going to talk about neutrons, but it's still not suitable for particle research. So in the end, I decided I should still come to this session because it's still, I mean, a neutron is quantum, I think. So, okay. So I should begin. So I'm now doing what is commonly known as ghost imaging. This started off as quantum imaging. My collaborators are from Shanghai Jiao Tong University and High Energy Physics Institute and also another company. So I'm afraid that the names are in Chinese. So first I should give you an introduction about imaging. I think everybody thinks, oh, I know all about imaging. Not necessarily. But what is ghost imaging? You have to know about that. Then I will talk about X-ray ghost imaging and then finally neutron imaging. I don't know if many foreigners are not aware that the earliest written records of imaging appeared in the Mozi, Book of Mozi, who lived 100 years before Euclid, and he actually did experiments in optics. For details, you can look up Joseph Needham's Science and Civilization in China. Okay, so what is well, we all know that to begin with,那个激光不灵，要点一下，哎，对，是激光，其实拿一个，其实这个也行，这也行，都是能 ，OK。So it's strictly speaking, it's a point-to-point relationship between the object and the image, because all the rays from this object should be focused onto the same point on the image. Then we say it's in focus. This is different from a shadow projection image. This is we know from all the shadows that's like we have in China, the shadow puppets, that's a projection. And it's still what we have when we take an X-ray photo of our lungs. That's projection imaging, not a real lens-focused imaging. So we know that when we take a picture in the camera, this is what we normally have. You have a CCD camera nowadays. But if it's a cloudy day or a foggy day, then we know you cannot take a good picture. So, what to do? Well, this is what the principle is about. 这个放在靠这里。我这个也不大好憋，我不知道是别在这里，别在这里。哦，这袋子上是吧？是。后头听不见吗？好了。So what we do is we put a beam splitter here. Notice that in this beam splitter. So here there's nothing in this path, and then although light goes through the object, through the scattering medium. 能不能用个红点？哎，好 Yes. This lens is not a focusing lens. It's just a collection lens. So it collects all the intensity and concentrates that into an intensity detector. We call that a bucket detector because it collects all the light. And then we do coincidence counting. This is familiar to those in particle physics. And after many exposures, we take the average sum, and then miraculously the image appears. but it's not a direct image. Okay, it's only an image in the second order correlation function. So that's the main thing. So we call this ghost imaging. Apparently this name was coined by Chen Yang when he visited the lab in the US. And he said, this is 鬼城, 很鬼啊 in Chinese. But if you translate that into English, it's ghost imaging. But it's quite different from the classical word of ghosts in imaging. This is what they use in classical imaging for another meaning. So this is based on, well, we know about the first order correlation and the Young's double slit. But what we are interested in now is the second order correlation, when we consider the image at two space-time points. So we call this intensity correlation. Okay, notice we also have an interference term here. So we are interested in G2, the second order correlation function. Now this was first thought of by Henry Brown, who is my hero. He was a test pilot in the Second World War, and then because his eardrums were damaged due to going through the sound barrier too many times, so he became a radar engineer, and then after the war he was a radio astronomer, and he studied photon correlation. The purpose was to measure the angular diameter of stars. Previously, they used a Michelson interferometer to measure that. But you know, that's phase sensitive, and if you go through the atmosphere, the phase is lost. So that was very a very difficult problem. So he thought of using this intensity correlation. And in 1 year's time, he published 5 Nature articles. It's on his work that the theoretical work of quantum optics by Glauber was based on. And Glauber acknowledges this in his Nobel lecture. It's a pity that Henry Brown didn't live long enough, otherwise he should have won the Nobel Prize as well. Okay, so the experiment was first realized in the US by Xi's group, and he used entangled photons from BBO down conversion. And this is a standard way of generating entangled photons. And you see here, one beam goes through an imaging lens through a photon and to the object, and the other beam goes through nothing. It just goes to a single photon detector, which is scanned, because in those days they didn't have a single photon EMCC. And this was the object, and then this was a reconstructed image in the second order correlation. And interestingly, this also satisfies a certain thin length equations, but the distances are from learned in high school. At first, they thought that this was a purely quantum phenomenon. And in fact, there was even a paper published in PRL that said that entanglement is a prerequisite for achieving distributed quantum imaging. But then this experiment was repeated purely classically. And this was done by Shapiro of MIT, and he called it computational ghost imaging. Now, we see that here, this is the original ghost imaging setup. But the purpose of this beam splitter, and we call this this is we call this sort of reference detector, CCD. The only purpose of this reference CCD is to record the field distribution of the light that is illuminating the object. That's its only purpose. We need to know the field distribution that is illuminating the object. So, if we know that already, we don't have to measure it on site. It was difficult at first, but then technology advanced, and we have what is called a spatial light modulator. So, with this spatial light modulator, we can pre-program the field distribution into it. But this is very common nowadays. actually we use another type of light modulator, which we call a DMD, a digital micromirror device. This spatial light modulator used to be made with liquid crystals and so on. So in this setup, we only need one detector because we have pre-programmed the field into this modulator already. So notice we have to know two things: the total intensity that is transmitted or reflected by the object, and then the field distribution, the spatial distribution of the field on the object. Well, we call this quantum imaging at first, and then the other names are what? Intensity correlation imaging, computational ghost imaging. But it's interesting that in the classical imaging field, they had also done similar second-order correlation imaging, but they didn't call it ghost imaging. They called it single pixel imaging, meaning that the detector is a single pixel bucket detector. And also in microscopy, they called it structured illumination imaging because the field has a structure, or dual photography. But anyway, to coordinate, we call this quantum-inspired computational imaging. This is what this article claims it to be. But they're all based on the Hamilton-Brown twist second-order intensity correlation. So with this introduction, I can just go on, and we can say that the chief advantages, as we said, as I just mentioned, we can image through a scattering medium. Recently, we can also see around corners. This has been reported by University of Science and Technology by Fei Hu and others. And the resolution can, in theory, exceed the radio diffraction limit of this same similar optical setup. This would need an area CCD. Single pixel detector, it can have much faster response time, greater sensitivity. So we can even take photos in very low light illuminations. This, you can imagine, is a great advantage in many fields. So even down to a single photon level. The disadvantages, of course, is that we have to, as I mentioned at the beginning, you have to take many exposures and then average over. So that requires a lot of data processing. But that's not a big deal nowadays because we have much faster computers. If we use the original non-classical quantum entangled light source, of course, that is very complicated and expensive. Unfortunately, if we use a true thermal light source, the visibility contrast is not so good because of a background constant, but this I will not have time to discuss. Anyway, so far, in theory, you can do this with any wavelength. And in our Institute of Physics in Beijing, we have, at first we did visible in near infrared, we are still doing some, and then X-rays, and recently neutrons. So, the first experiments were conducted by Shanghai Institute of Optical Fine Mechanics, and also in Europe, and also in Israel. But they used very simple two-dimensional targets at most, and also they had to go to very large accelerator facilities, like this one in Europe. You see that their object was just a very simple wire, and that is a reconstructed wire. So we were the first to do this in an ordinary lab with a tabletop setup. That's all it is. X-ray, common X-ray source. And the interesting thing is the modulator, we just used a piece of sandpaper, ordinary sandpaper. This. The point is you have to recalibrate, pre-calibrate the optical source field like this. So what we did was that we have a CCD, so we translate the sandpaper step by step, and we have many exposures, but then we re-record that into that computer, and then we repeat the steps at the same stage, and then illuminate our object. Each exposure frame is only 1 microsecond, so although we had to do many exposures, the total time is not very long. So this was our first experiment, and then we did a real object, a shell, a real three-dimensional object. This was for a similar projection photo after 10 seconds. This is what you get, and this is what we got. It looks very not very promising because you have 10,000 exposure frames, but as I said, each exposure frame is very short, so the total exposure time was only 10 milliseconds. For a similar 10 millisecond projection image, you can see the image is barely visible. This is a contrast to noise ratio with it. And the total flux is per unit area. If you calculate that in terms of the CCD pixel size, it's only just 1 photon per pixel. Now, for an ordinary camera, it cannot respond to less than so many pixels. So this was reported in the Science Depth. The main feature is that we can lower the X-ray dose. So you can think what a great benefit that would be in hospitals for patients and doctors. But Shapiro did say that it's got to be a good image, of course. Ours is still not so good. So we improve the resolution and reduce retrieval time. So our aim was to achieve 10 micron resolution. Before that was 100 microns. So why 10 microns? Because cancer cells are 10 microns in size. So this is what led our experiment. We changed the modulator from ordinary sandpaper. That's a random pattern, speckle pattern. So this is a known Hadamard pattern. So these patterns are mutually orthogonal, so you do not waste exposure times. And this is pre-programmed, and the resolution now depends on the size of the pixel of your Hadamard matrix. So this we could reduce down to 10 microns. So this has been published. This is an illustration. At first, we just use a copper PC board to do the experiment. That's not so good resolution, but then we used gold. We specially fabricated this modulation mask. And this we could, with 64 by 64 pixels. Each pixel is 10 microns in size, and total. Now you don't need 10,000 exposures anymore. We only need 200 or so. And this is what we've achieved. So you can see that the resolution, this is 150 microns, and then this space here, this is 10 microns. And of course, we also used AI and neural network, etc., etc. So then we later did spectral ghost imaging, energy selective, and plus deep learning and all that. So then another kind of spectral imaging is based on resonant absorption imaging. So when you have different elements, they have different absorption edges. So we choose molybdenum, silver, and tin. That was the original object, and this is a reconstructed object. So you can see at different energy levels, different species appears clearly. This spatial resolution is 100 microns, and the spectral resolution is 0.3 kiloelectron volts. Now, neutron radiography, maybe some people are not so familiar, but it's very, very useful in materials analysis. But to shorten exposure time, you need high intensity, and high intensity, of course, may damage the sample. And also you have to go to large accelerator facilities. So with neutron ghost imaging, we can reduce the flux and improve resolution. Of course, how can you modulate neutron beam? The problem. And we still have to go to larger accelerator as neutrons. And basically, the main thing is the modulation. We prefabricate this mask and then we etch holes and fill the holes with an oxide because that absorbs neutrons. So it's an absorption mask. So this was our object the object was made of cadmium. Resolution is 100 microns. This is pretty good for a new radiography. And even if this, although their particles they're not light, so their speed is different. So we use the time of flight to perform the resolution analysis. And then also we did the resonant absorption of neutrons recently with 3 different materials, stencils stacked together, NGI, of indium, silver, and tungsten. The mask is filled with the powder of the same 3 elements in a certain ratio. And this is a reproduced image. Okay, so this is a summary that ghost imaging has a great potential for all kinds of uses, and in fact, in our also internationally, there's great interest in developing ghost imaging. Thank you.
我刚刚今天这个有介绍到这个胡定南老师，胡定老师我们中国物理学界的一个传奇人，应该是我们量子光学最早的一批的开创者之一。然后胡老师颁授一年正角奖总共100回收，400
So yes, I think this is rather a new field too. So maybe you don't have many questions. Okay, thank you. 这个退出来，这个怎么退出来
So our next speaker is Professor Tan San from